from Luis, who will speak about nonlinear fractional diffusion equations, two problems with free boundary.
So, thank you to the organizers of the seminar for giving me another opportunity of talking about these things. Okay. For many years I have been involved with a huge number of people in trying to understand the regularity of porous medium equations with free boundaries and similar equations like Stefan, Hirshaw, P-Laplacian. So there's a group of equations that make evolution with a certain degenerate or singular character, and then they produce free boundaries. And the idea is that fractional diffusion began to be popular among people in PDEs, at least in the group of Luis Caffarelli, around 2005, and more or less people around were pushed gently or non-gently into understanding parts of the theory, and I was one of the persons who started working with Luis in 2007 when I was visiting him on fractional diffusion. And what he told me, this fractional is interesting, but I say, I'm just interested in free boundaries. It's okay, I will look for a free boundary for you, and I will tell you which one. And then I have been studying another, there are two main models that we have been studying. And since the theory was completely open, it takes a long time to develop the basic theory. So we didn't do many free boundaries. What I will tell you is that there are problems on free boundaries that were stated like at the beginning and still are not solved because we lack the technology and the time to do it. So it's question of more people to step in. Okay, so let me tell you now, just to remember things that you already know, because this is part of a presentation. The porous medium is this heat equation with an exponent u to the m, and m is larger than 1, and if you differentiate, you get a form of heat equation with coefficient that depends on the density, and this coefficient is mu to the m minus 1, so for u equals 0 it is degenerate, and this is the problem, that it degenerates and creates a slow diffusion for densities that are small, while intermediate densities propagate perfectly and even higher densities propagate even better than in heat equation. So the interesting question for mathematicians is to understand what happens for u next to 0. And this what was important when this equation was proposed. In many, there were many motivations, from fluid mechanics, from plasma physics. In plasma physics, they were interested in very high temperatures, and they were very interested in knowing, not that the high temperatures propagate quickly, they already knew, the border between high temperatures and the cold surrounding atmosphere. So for m equals 1, you get the classical heat equation, you have the idea that maybe you can use perturbation methods. And in fact, you cannot. This is not a nice perturbation of the heat equation, and almost none of the results that you want to get concerning regularity and free boundaries come from saying, let's take the heat equation and let's put m equals 1 plus epsilon. It doesn't work. And next thing is that if m is less than 1, the equation is still interesting, but then instead of being degenerate, it's singular. And this is called fast diffusion. And it was proposed in physics at the beginning, but not very convincingly. And recently it was discovered that this is very important in geometry because it's related to Yamabe flow. And it is important in functional analysis because part of the Sobolev inequalities and so on have evolution versions with fast diffusion. Okay. The general idea of studying these problems was put forward in the 60s, so 50 years ago, by people like Jim Serring, that explained once to me that in fact there was the idea of writing a book about this equation, explaining more or less what happens when A, B, and H are, for instance, powers. And the book is not written because even in the case of the porous medium equation, it took a long time to write down the mathematics carefully. So it's impossible to put in one book the whole immense amounts of information that is being gathered about the system's regularity, uniqueness, free boundaries, asymptotics, singular points. So you have to concentrate on particular equations, which is something that people in functional analysis really don't like, but people in PDEs accept it. And let me tell you why I use this derivation. I will use it later a bit just to fix ideas. Porous medium is just an equation that starts with the basic conservation of mass, the basic transport equation, but the velocity is given by the gradient of a certain pressure, so it's a potential flow. And this idea is what is called Darcy law. And then if you have a gas, you say that the pressure is a power of the density. And this is the simple way of closing the system. This was done by the engineers in the 1930s, and even the Darcy law was proposed much earlier by Darcy in 1856. And the equation as an equation for gases in porous media, because Darcy law is an equation that replaces Navier-Stokes in porous media. This was done by Muscat and Levinson in the United States and Russia in the 1930s when they began to do calculations for the oil industry. This is why they were interested, but they could not solve it. And it took like 20 years to begin solving it. They began solving it in Moscow, and the existence of solutions for porous medium was done in this group in the Faculty for Mathematics and Mechanics in Moscow, in Lomonosov University, by Oleinik and her students. Okay, so if you put the P into the V and the V upstairs, you get this simple computation, and what you find is that this exponent M is 1 plus gamma, and gamma comes from the gas law. They can be 1 or larger than 1, for instance 1/4, and this here is 2 or 2.4. So it is never 1, it is much larger than 1. And there is a free boundary. This is what they were interested. The propagation of temperature according to porous medium has a big ball of flame and something that separates from the cold surrounding atmosphere. Okay, and so the idea is that I will not talk about this, just the motivation. There are enormous amounts of people who work for, I began to work in these things in 1981, and we have been working non-stop until 2000, when we discovered that something that was not done before, entropy methods, could be done. So for 6 years we did entropy methods like crazy. And then I went then I spent some time writing a book that you can find. And it was impressive because in writing the things I knew about the only one equation, it took 620 pages. And I didn't know what to do with the research. So the people in Oxford who were very nice told me, why don't you write it and submit it to us? And it was another 250 pages. So it's amazing that the mathematics is so complicated just for a simple equation. Since we have like 20 models going on, it implies enormous amounts of techniques that have to be combined. Okay, I wrote a survey about asymptotic behavior that is very short, and then we wrote these functional analysis things with Bonforte, Dolbeau, and Grillo in 2010. But let me tell you about this different thing, what I want to talk today. You have fractional diffusion instead of standard diffusion. What do you mean by that? And you mean that any time that you are using Laplacians, you will use fractional Laplacians. Well, that's not really true. In fact, the model that Caffarelli proposed to me was not doing that because there was no way to recover the free boundary. And he had been reading some works in statistical mechanics where you find these models where you have free boundaries. The idea is the following. Let's go back to porous medium. You still get that U is density and V is velocity field, and you get the conservation law, which is the transport equation. And then you still say that V derives from a potential, okay? And then the question, the only open question for me is that the potential is different from before. So if you take the same potential as before, then you get porous medium. On the other hand, if you take a potential and you say that divergence is 0, then you get Laplacian equals 0 and you get Hill-Shaw. So playing with densities, potentials, and velocities makes you able to derive different models if you stop the derivation in different lines. And I think this is interesting because of the modeling. Writing sensible models is important in what we do. So the idea that Caffarelli suggested to me, based on what he had been reading, was changing the last part of the derivation of porous medium, where you say that the potential is the pressure of the fluid and is the power of the density according to the gas law, by saying we are not talking about gases, we are talking about some particles or densities according to some statistics where you get long-range interactions. How do you do it? And then if you have been listening to people in chemotaxis, the idea is also used in chemotaxis. Chemotaxis is certain bacteria that move around by diffusion, and also because they have a chemical potential that moves them around. And the chemical potential comes from created by the density. So there is something called the potential that is created by the density, but not by one element. It's created socially. And this is the point of long-term diffusion. The idea is that in order to create the potential that will drive the flow, you make statistics with U, and you integrate because you want to consider that P will be the result of applying a certain convolution operator with U and putting the people who are next to you with priority over the people who are far away from you. And this is just taking a certain Markovian process with a density that is not local but is widespread. Now, there are densities in the Markovian processes which are characterized by the densities that contribute to the theory of Levy processes. And they are combined with diffusion plus jumps. So you are thinking that there is a probability of jumping far away. The idea is that in the end of this story, if you want to summarize this modeling, because I don't have time, but it's written in many of these works, the idea is that it is sensible to use this Laplacian minus S, where it has a convolution kernel, which is this thing. And n minus 2s is the way of representing the fact that you are not using the potential, the Newtonian potential. In fact, if you put n minus 2, then you are saying that it is a Newtonian potential. And you are doing like chemotaxis, but with the other direction, repelling chemotaxis. So we are doing like fractional chemotaxis in the repelling way. Not in absorption, but repelling. So this is it. There is nothing really new. So the idea is that since we are now already using the potential in the repelling way, we don't need to put extra diffusion to close the system. And the system says that ut equals divergence of u gradient p, and p is k of u, and if you replace the k by what it is, you have this formula that looks like many formulas of higher order equations. But in this case, it is not higher order, it's lower order. You are interpolating between no derivative and two derivatives, while thin films interpolate between two derivatives and four derivatives. So this is the point. We are going back. The potential is a regularizing potential, not a complicating potential. So this is very different from the Canhillier, because we are in low derivatives. The number of derivatives is 1, 2 minus 2s, which is larger than 0, so we still have a differential operator. So you put initial conditions and you solve it. And we wrote papers that took a long time to publish and to write. The first paper was written in 2007, and then, it was announced in this free boundary conference in Stockholm in 2008. But then we took some time to write it. And then we proved asymptotic behavior in the second paper and the regularity in the third paper. And let me tell you now, because maybe we have time to discuss this thing, how many people have seen carefully these fractional ablations? Should I jump on it or go through it? The idea is that fractional Laplacian has different definitions, and in Rn they are all equivalent. So you can use any of them depending on what you want to do. So you get different proofs of the same results. Or maybe you get one proof for one result and another proof for another result. And this is interesting. The first idea is that since it is Laplacians, you use Fourier analysis in the whole space. And the multiplier is C to the 2s. This is the symbol. But if you don't want to go to Fourier operators, for instance, because your equation is nonlinear, then you want to get a representation of the Laplacian as an integral, as a convolution integral with a singular kernel. In fact, this is too singular for us. I was using minus s, so here my operator was a minus, but if you do the direct Laplacian, fractional Laplacian, you have a plus here, so the singularity is too singular to be well defined for x equals y. And then you need, in order to define this, put this ux and assume that u is C alpha. So you can kill this singularity. You take a principal value. So this is what you call a hypersingular kernels. It is not a kernel, it's hypersingular integrals. So this definition is very good at infinity. It's only a problem of using the regularity of u to kill the singularity near when x minus y is near 0. And so this is just a question of harmonic analysis again. The next thing is that maybe you want to do the approximation with discrete jumps. And then you say that any time that you integrate your equation in time, it's like making a step of the Markov process. And the probabilities use the famous rule, you call it Kolmogorov rule. Un minus 1 at the time step n plus 1 at the node j is a certain mixture of the probabilities of the other points before plus multiplied by the transitions. And the transitions have precisely this shape. And then you define the process as the expectation of the difference of these values of the function. Now there is another way. It was the way we used. So probability we were not using, let's do some harmonic analysis. In that case, you can say that for s equals 1/2, let's say minus Laplacian 1/2, which is one derivative. In fact, you can extend artificially your function to the upper half plane, invented upper half plane. Let's say invented because it's a way of talking. Here you have your standard x belonging to Rn, and then you have a function that you want to take the Laplacian. What you do is extend this function in a harmonic way as a certain potential outside, and then take the gradient, the derivative of Laplacian with respect to the normal. And this is the first derivative in this strange way. It corresponds to taking the Laplacian 1/2. If you do it again, and you do again the normal, then you get the second, doing twice the operator on a certain function u, you get the normal of the extension, which is the second derivative of the extension. But since the Laplacian is 0, it minus the second derivative in x of the extension at y equals 0. So it's minus the second derivative of x of u. So you prove very easily that doing this Dirichlet-Neumann operator twice, I mean, you have to revise the proof because I am cheating a bit. You will get something that is Laplacian twice in the vertical direction, which is minus Laplacian twice in the x direction, which is the minus Laplacian. So this is square root. And in fact, this justified, you have to justify that this formula is the same as the formulas before. Now, what do you do if you don't get, if you do not have the special value s equal 1/2? Because this was known from many years ago. What Caffarelli and Silvestre proposed is to use a weighted extension. If you put a weight that is 1 minus alpha, then in alpha is 2s, then you can get the Laplacian s as a certain weighted normal derivative. So you get the theory of harmonic extensions with weights, and you have to think about all the theory of traces in weighted spaces, and you develop the theory. And the idea is that now you know that you are doing something that has to be in agreement with the harmonic analysis that says, in harmonic analysis, that you are multiplying by c to the 2s, so you are in the fractional spaces of the form ws. Is this compatible with the theory in the spaces ws? In fact, you prove that this is compatible. Okay. So what do you do if you work on a bounded domain? If you work on a bounded domain, the Fourier definition doesn't make any sense. The rest of the definitions can have different interpretations if you get different operators. And this is interesting because you have to do the proofs according to them. There are beautiful books to read this theory. For instance, Lankov in Russia and Stein in the United States. And then the functional analysis of the operators is Davis. In fact, these operators are very good self-adjoint positive operators. So you can do the theory if you need. So let me try to see what we can do with my equation. My equation was exactly ut equals O plus divergence of u gradient of k of u. And k of u, you can call it p. And it's the minus Laplacian minus as of u. Now, if you put s equals 0, this is the typical porous medium. There is nothing new, and you get the free boundaries. If you put s equals 1, then you are going up 2 derivatives, and you are going down 2 derivatives. So the equation is of order 0. And if you make the computations carefully, you discover that you get gradient u, gradient p minus u square. So the minus u square is okay, but this is a curious thing because u is differentiated and p is differentiated, but p is twice integrated. So there is a combination. The whole operator is order 0, but since it is nonlinear, it is unbalanced. And this is something that was found, the Newtonian potentials, this is what we are doing now, is found in hydrodynamics as a model for superconductors. So there was a connection with superconductors. But it is no more diffusive because the order of derivation is 0. Now, in one dimension, this thing is not so difficult because everything is differentiated with respect to x. So what you do is you integrate u once and call it v, or differentiate p once and call it v. And then you write the equation for v, and you find that it's Burger's equation. So in one dimension, this thing in the level s equals 1 is Burger's dimension, which is not very difficult, but it has chunks. So the equation with this potential, the case s equals 1, will have shocks and no regularity. The question we wanted to know, Caffarelli and myself, is can you do a theory and will it be regular? And the idea is that maybe if you integrate once, the idea at the beginning was that you integrate s equals 1/2, the order of differentiation is 1 derivative, 1k, so 1 plus 1 minus 2, 1/2 equals 1. Maybe the order of differentiation is important, and when you have s equals 1, it stops being regular. And the conclusion of our analysis is this is not true. It will be regular for all the s until s equals 1. Okay, so using fractional Laplacians was lots of the work was done in the elliptic or in the probabilistic framework. The elliptic framework, Caffarelli and Silvestre did a lot with the rest of the people in the school. In fact, you mentioned them. And in the case of the parabolic, there is all the people in probability. In fact, if you use kernels that are not as large as my kernels, because my kernels have big tails, if you use a kernel that is a compactly supported function, this is a way of regularizing the porous medium. And it has no big deal The problem with this thing is having kernels that are very big at infinity. So there are a number of people who contributed. Let me jump on that. This is the general equation that was found in these books in statistical physics, which has a certain power of rho here and has a certain other power of rho here. We did, let's put rho and rho in both cases. So what you prove is existence of weak energy solutions, and you prove the property of finite propagation for the model with Caffarelli. So this is what I wanted to present to you. There is a solution with finite propagation. The next thing is that we proved that there were some similar profiles and they were compactly supported. And the idea that we did was the typical idea of using renormalization, passing to the Fokker-Planck equation and trying to solve it, and using entropy methods. And this is the second paper. And then we proved the regularity in the third paper by the typical processes. L1 implies L2, L2 implies L infinity implies C alpha. And this is the last paper. So then we did the limit S tends to 1 in a paper with Sylvia Serfati, trying to understand how in the limit you lose the regularity when S goes to 1, because it's no more a diffusive equation. We did this paper, and there is a general survey of the things we did. So let me now use this moment to present to you the problem. Suppose that there are solutions, and the solutions, you can construct a solution that has a certain regularity, belongs to the LP spaces, etc. So assume nice theory. Okay? You want to know if there is finite propagation or not. Okay. So if you write the equation of ut plus divergence of u times v equals 0, then the idea is v has to be L infinity. And this is a propagation equation. You prove that the velocity field is L infinity, then the solutions will propagate with finite speed. Now, suppose now that U belongs to L1 inter L infinity, which is typical of diffusive processes. And we can prove this thing. We prove that for certain of scalars of solutions, there exists a solution that belongs to L1 inter L infinity. In that case, then V is a certain kernel applied to the derivative of a certain kernel of U. Okay. Because remember that P is K of U and V is minus gradient P. So let's put minus. Now, this is a derivative of an integral. So you have a kernel that takes U in L1 inter L infinity and goes up to P that is better, and then differentiates. That is worse, and you get V. Now, you integrate 2s times. You differentiate 1 time. So this operator is integration of 2s minus 1 larger than 0 if s larger than 1/2. Okay? So if s is larger than 1/2, you discover that this looks like a transport equation from the point of view of the velocity. And you expect the velocity to be a nice velocity corresponding to U belonging to L1 and infinity, and dxk is a certain kernel that has the good properties to prove that V belongs to L infinity. Okay? So this is a proof. But the proof asks from you to believe that S is larger than 1/2. So this is this wrong idea that we had for a time, that S equals 1/2 is the limit of transport. So this is the first idea. Now, second idea, can you do something that is good for all the values of S? Well, you do the typical things for diffusion equations and try to see if you can justify for every S. And the idea is that the equation ut equals that of U gradient K of U admits similar solutions. And maybe a similar solution will be an example with compact support. Now look at this. You put u equals t to the minus alpha, f of x t to the minus beta. And you want to select first the plug into equation, and choose alpha and beta to eliminate time. Second, use integral of u dx equals constant, and this implies that alpha equals n times beta. This is a typical thing that you do when you get the formula for the Gauss solution or for the Barenbrad solutions. In this case, alpha is n over n plus 2s, and beta is 1 over n plus 2s, n is dimension. And then the important point for me is what the equation for, let's call y the variable x t to the minus beta. I want that everything will be a function of y. And what I get is divergence of f, gradient of k of f equals the terms coming from here. And the terms coming from here are beta, and this is the confining term coming from ut. And this is what you call the Fokker-Planck term. This is very well known in the approach to parabolic equations using functional methods. So then you get this equation. And this equation is strange because it has gradient k. You don't know what to do, unless you have been working with these people in Paris. Then, this is what I was doing at the time. You take f outside, and you get kf plus beta over 2y squared equals 0. Okay, and one step more, and I am in your talk. Let me do this step. If the Laplacian is 0, and I am looking for a special solution, I eliminate the Laplacian because I assume that my solutions go to 0. The fact that they are radially symmetric, there is only one that has to be divergence equals 0. Now I have f gradient of kf plus beta over 2y squared equals 0. And let me call k of f equals p. Then there is this alternative. Either f is 0 or gradient of p plus beta over 2y squared equals 0, which means that p equals c minus beta over 2y squared. One of the two things has to be true. But then you discover that f is equal or larger than 0, because your problem is for positive solutions. And working not trivial, you prove that this obstacle, p minus f, is larger than 0. And then you get an obstacle problem. And the obstacle problem says that either f is 0, f is the Laplacian s of p. I mean, minus Laplacian s of p. P was the s potential of f. F is minus Laplacian of p. So this is the obstacle problem. This was what we discovered in November of 2007. And then I went to Luis and said, listen, this is the Fokker-Planck calculation that you told me to do. Do you know how to solve this? He says, yeah, it's in the paper that we are writing. So this was 2007, and there was a paper by Caffarelli and Silvestre, where they prove there exists a unique P that goes to 0 at infinity, such that P is C1S. And F, which is Laplacian S of P, is belonging to C1 minus S. So there is a solution. Now, what is that type of the solution? It's very curious, because P is not now proportional to F, to rho. I mean, remember that I call it rho, and I then went to U, and the sensibile variable is F, but they represent the same quantity. It is not true, as in the porous medium, that U and P, the pressure, will be proportional. There is a certain relation through the kernel. So if you go to the obstacle problem, this is the obstacle, and this is the P. It has a coincidence set, This is the coincidence set, the support. And here, outside of the coincidence sets, P is larger than the obstacle, and F has to be 0. And the graph for F is like this. Here, in this support, there is a certain F, which is the Laplacian S of P. It cannot be as regular as P, because P is a parabola, and this is something that is not as good as the parabola, so it has to be different. And in fact, the question that we have is, what is the shape? Then we discovered that in fact, in a paper that was published in 2010, but was circulated before, I got it in 2008, there was a work in one dimension by Karch, Monod, and Biller. Biller, Karch, Monod, sorry. It's the order in which I talked to them. And they discovered that using a beautiful property that was known from probability, they can find explicit solution. They found this idea, L, 1 minus S of 1 minus x squared, 1 minus s equals constant on the support. And I pretend that 1 minus x squared, 1 minus s can be f. And then what I do is I say that the Laplacian of the pressure is minus constant, right? But minus Laplacian of the pressure is constant. But minus Laplacian of the pressure is the Laplacian S of the Laplacian 1 minus S, sorry, of the pressure. I want this to be constant, right? But L minus 1S, Ls of P is F. So I want to be constant. So the idea is that my guess is, if I have a function whose 1 minus S Laplacian is C, I take the quadratic potential, I decompose the Laplacian in two parts. One of them says that Lf of P is by definition F, and the other one says that L minus SF equals constant on the support. Now, the problem is that L1 minus S of F is outside. But then I get my complementary principle. The equation is multiplied by F. There is an obstacle problem, you don't care what happens outside. So this is the way of finding the solution in explicit form that solves the obstacle problem and proves that a certain function of this form is the similar solution and has compact support. If you look at the profile, it will have a form like this, and here it will be 1 minus x squared to the 1 minus s, which behaves like distance to the 1 minus s. It will be further 1 minus s, which is optimal. So the optimal regularity of the obstacle problem is reproduced, this is the paper by Caffarelli, Salsa, and Silvestre. It's reproduced in these explicit solutions, right? They cannot be better than that, and they are explicit. And the idea is that the solution, if you put this time in this x, has the typical support of the Barenblatt profiles, but the rule of expansion is x behaves like t to the beta, and the beta depends on x. The only difference is this. So you have solved the obstacle problem. Now, once you solve the obstacle problem, my question for you is this enough? Is enough to show that this problem has finite propagation, at least for one solution? What is the next step? Next step is proving that for reasonable initial data, there will be a free boundary all the time. How do you do that? By comparison. Can you prove a comparison theorem? No, because this is a transport equation. So next step of my investigation of the free boundary problem is, can I use this explicit solution to get finite propagation theorem for every solution that is, let's say, like this. Suppose that u naught is a certain function that is continuous, bounded, and compactly supported. Can you prove that it has finite propagation? You put some of these monsters on top, and then you compare, but you cannot. So we didn't get comparison.
Because it is false, or because you don't know how?
Comparison is false in general because it's a transport equation. So if you want to do comparison, you have to do something. Let me tell you why it is false. It took us some time to discover this example, but in the end you have to discover the example or die. Suppose I have my original thing that will spread with time like this, which is just a similar solution spreading with time. So it's moving out. And you can prove that initial data that are symmetrically decreasing will do this is moving out. Now suppose that in this thing that has long-term influences, there is this big friend. It's like the big friend in the, this is like Putin. Okay, there's a big friend here. What is the effect of the big friend? In the original propagation with porous medium, no effect because it's local. Until they meet, there is no influence. But now, the velocity here is v1 plus v2, where v1 is the derivative in x of the kernel applied to u1, and v2 is the derivative in x of the kernel applied to u2. Suppose that you put a certain time t0 and you update your velocities. The total velocity of this combination of the two mounts will be whatever happened before plus what happens due to the velocity induced by the effect of the other guys. And the other guys are pushing you in this direction. So what happens after the effect of the friend is that instead of being here and moving here, you were here and you move here. There is no comparison. This solution is less pointwise than this, and the result is that before this went to here, and now it goes to here. It's not comparable, right? It's a question of transport. Can you do something like using Lagrangian coordinates? Writing the Lagrangian coordinates after changing transformations with fractional ablations is not very nice. But in one dimension, there is a trick, which is there are two tricks. One trick is by Ambrosio and company, and you use Weierstein, sorry. And after yesterday, German names don't get in my head. Weierstein method. And you do transport. Another way is doing indirect transport, which is doing the what you call the mass function. Define, and this was done by Miller and Monod. Define the function v equals integral of u from minus infinity to x, which is, you call it the mass function. And you realize immediately the vx equals u, and then the equation for v is vt equals integral of u v, oh sorry, let me call it this w, or m, the mass function. Then mx, so mt is the integral from minus infinity to x of u vx, which is u v, which is mx k of v is the derivative in x of k of u, k of u xx, so it is mx k mx. And this can be seen as a fractional version of Burger's equation, because it has like mx squared, right? It's like a Hamilton-Jacobi. Now, for this equation, for the m equation, you prove comparison. in 1D. Once you prove comparison of the masses, then you can compare the masses, and the free boundary is the first moment when you find the mass. So what is the open problem? Can you, at this moment, I still didn't have a proof that the solutions have finite propagation for S less than 1/2. So let me try to do the idea that we use with Caffarelli. The idea is that there is no comparison, but these ideas that happen to you if you work with Luis Caffarelli. There is no comparison, but there is something called his comparison. And the idea was to use a very, very, very big super solution, which is extraordinarily super solution, and use the viscosity method. Use the viscosity comparison with a certain function u that is like c times c1 times c2 minus x squared. So it's a function like this. And you try to find your function here. And what you want to prove is that C1 and C2 are chosen so that ut can be compared at the point of contact with ux and uxx. See why I need ux and uxx. Tell the equation. Ut equals u p xx. So u xp x plus u pxx. Okay, let me do it in several dimensions, which is what I have to do. Is gradient u gradient p, which is gradient u gradient p plus u Laplacian p. And then you have this, and you have this. And you want to compare this solution at the point of contact. This solution will be a solution of the form ut equals gradient u a of xt plus u b of xt. And a is gradient b, and b is Laplacian p, which are kernels. Okay? So this is like a linear equation with coefficients. What I want to prove is that in my solution here will satisfy ut equal or larger gradient u with a plus u with b. How do I do it? Because the gradient u has a c1 c2t minus x, and gradient and ut has c1 c2 minus x c2. And in order for gradient u to be very big, I choose c2 very big. So this thing is going away very quickly. I put a super solution that moves very quickly away, so that at any given point, the linearized version of my equation, when I want to compute by comparison of viscosity solutions, this will be a solution, and this will be very big super solution they cannot touch. So you cannot touch u. And the whole question is, can you make the analysis of the behavior of the potentials near the touching point? What I prove is that you touch a certain parabola. From below, all of these coefficients have the right bounds. This has to be bounded above, and this has to be bounded. This is easier than this. You cannot get a bound for the Laplacian of p, because it's integrating and then differentiating twice. You cannot do that. But you can get a certain bound that cannot be very positive, because it's touching from below. That's the point. Even the locally cannot be very positive, because it looks like Laplacian. Away, you can calculate what are the behavior. So I will not enter into the details, because it's in our paper, first paper with Caffarelli. There is a proof that says that if the solution is a certain quadratic traveling wave with high speed, you can calculate the linearized version with a certain coefficients here that I control, and I prove that it cannot touch. So the idea is that there is a free boundary. What is now left for me? I have proved the free boundary in the whole set of cases, but I have no theory about what the free boundary does. In particular, the free boundaries can move back and forth. This example shows that this thing, it can move this way, right? But this thing can move this way also. So they move backward. So the problem that has not been done in all this period is problem. Take U naught belonging to continuous and bounded and compactly supported, and take equation ut equals divergence of u gradient of Laplacian minus s of u, and study regularity of free boundaries. This is an open problem. Okay. You can get estimates in one dimension. In 1D, study integrated equation, the M equation. And remember, the M equation is MP plus mx, a certain operator k of mx equals 0.
So what is known in one dimension?
Well, there are free boundaries, and there is comparison for the M equation. Okay.
Do you know anything about the regularity of the
No.
free bound?
No, I'm honest. This is a problem to be solved. Okay? So this is one problem.
What's the intuition?
The intuition is that the free boundary is there. It looks like the regularity of the free boundary, I mean, the lateral regularity is held there. And then, how do you write something that linearizes Hölder? You want to do something with linear analysis in some variables, right? Okay.
So in higher D, you don't
Higher D, we don't know, we
you
don't
don't
have
even know-
comparison.
you
It's
don't
even
even know
worse.
if there is a free boundary.
We know that there is a free boundary because we proved that the solutions propagate at finite
So
distance.
this is the big brother there works also in a higher dimension.
Yes. Yeah. The explicit computation with the obstacle problem and the explicit solution are in all dimensions. So there is one solution that is good to be tested. There exists a solution that you can test, which is what we call the fractional variable. We call everything variable now.
The trick consisting in introducing M resembles the change of variable from Lagrangian from Eulerian frame to Lagrangian frame.
That is true. So everything seems to be good in one dimension, maybe after integration.
Because for the Porous medium equation, I have learned it from Tartar 30 years ago, and I applied it to compressible Navier-Stokes equations in one space dimension to get.
Yeah. In fact, this equation for M looks a bit like a P Laplacian equation. You mx mxx. I mean, if you integrate porous medium, you get P Laplacian in one dimension. In several dimensions, you don't get anything. Several dimensions is bad for doing this kind of Lagrangian tricks unless you do transport. Now, the operator is not very good to do transport in several dimensions because it is not technically, they call it geodesic convex. So you cannot do this approach à l'Ambrosio, etc. But in one dimension, you can do it. And this is something that in one dimension, the idea of approximating these things by transport was done by Jose Antonio Carrillo with some students. just showing that the transport approach by Ambrosio works. So there is a hope that in one dimension you're going to do much better. Okay. Okay. So if I have 5 minutes to present the second, yeah, I promised the second problem, but maybe it's enough. I go?
5 minutes.
Okay, I have 5 minutes. The speaker will never forgive.
Not more, because the pizza is getting cold.
Hey?
Pizza is getting
No. Okay. Second problem is the model number 2. It's very strange. Model number 2 is doing ut plus minus Laplacian u equals 0. This is the fractional heat equation, no monkey business. This is the real thing, that they do it in probability. And minus Laplacian, you put s less than 1, this is the fractional case. Okay? You put the minus here to be a positive operator and you solve. And you put u equal u naught in L1 or in LP or in L infinity, and it works. The idea now is the second model of nonlinear fractional heat equation is ut plus minus Laplacian s u to the m equals 0, and m larger than 1. And in that case, there is no finite propagation. The equation is very nice, it generates a semigroup, there is no finite propagation, and there are some similar solutions, but the similar solutions are like this. And they have a tail, and the fractional tail is x to the minus n plus 2s. They have a tail that does not depend on n. The tail of the Barenblatt solution. I mean, there is a solution of the form t to the minus alpha, f of x t to the minus beta, but in this case, the f has a tail. Now, a very curious thing happens when m tends to infinity. The solutions have a tendency to do this thing. This is called the Mesa problem. And the Mesa problem, in the end, is an obstacle problem also. So can you do the Mesa problem for m tends to infinity and s between 0 and 1? And this is the second problem in which we're working now. The idea is that if s equals 1, which is the porous medium equation, the end of the Mesa problem is a solution like this. And if s less than 1, the end of the Mesa problem is a solution like this. It has the fractional tail because it cannot get rid of the tail. M goes to infinity, s in intermediate, you get a tail. So this is, let me call it, this is the fractional f, and this is f for s, and this is f for 1. And the Mesa problem has been studied by Caffarelli and Friedman and a number of people around the 80s. In particular, here in England, there was work by, the work was begun by Ockendon. And you were involved also?
Yeah, as was Charles.
Or you were there?
Charles,
Yeah, and Herrero. Okay. You did a paper on, the first paper where the model was derived with this idea. And then there were papers by Caffarelli and Friedman proving that these things are true. Now the question is, why is this problem related to that problem? The idea is that this tail comes from an obstacle problem where the idea is that P has to be equal or larger than a quadratic obstacle. There is a certain pressure. And that there is another function that is not f, that is g, that is 1 minus x2 to the 1 minus s. So what is the relation of these things? And now the idea is that the f is the limit as m tends to infinity of the profiles fm s of y for m finite. And the g is the limit as m tends to infinity of the m fm to the m of y for m finite. And you pass to the limit. So it is a very singular limit. You remember, Charlie, that you did these things. And now the p is the integral. No, they did it in s equals 1. The p is a very strange pressure that comes, is the integral of r, fr, differential r, between r and infinity. At the beginning, the pressure touches here f touches the border, and this is r squared, and there is a c minus. No, that's like this. Yeah, so this will be c minus integral of 0 to r of r fr differential r, and at the beginning is c minus a r squared, and then is larger than c minus a r squared. So there is a way of choosing in this limit the profile, the function that represents the inner behavior here, and the pressure, so that the problem here and the problem here are the same. And the conclusion is that the obstacle problem with the quadratic obstacle is very important in many of these problems of nonlinear diffusion. And we have been studying, this is one of the things we are studying now, is why you have all the time the same obstacle problem with a quadratic profile. What is the open problem here? Suppose that you get initial data ut plus minus Laplacian s of um equals 0 with initial data u0x independent of n, and you pass m tends to infinity, and it is a very general function. What can you get in the limit? Because this was done on the basis of taking the Dirichlet data. If you don't take the Dirichlet data, what is the limit? The limit will be probably an obstacle problem that is not the same I have solved. Maybe the obstacle is not quadratic. So there is an obstacle problem as the limit of these free boundary problems, and the Mesa diffusion in this case will be a new obstacle problem. And this is something we are doing now, trying to understand fractional Mesa problems as obstacle problems. So this is the second problem. Okay.
Did you mean to write that parallel as independent of n?
Eh?
Is that parallel really independent of n? To your left, down a bit.
Here.
Yeah.
Yes.
It's independent of n.
Yes.
Yeah.
It's just a. Yeah. It will be independent. Yeah. I mean, it depends on if you take f or fm. The variable is f. F will be like this. And in fact, this is. Okay.
Yeah, but then alpha and beta.
Yeah, the alpha and beta depend on n,
Yeah.
but not the profiles. The tip of the profile at the end is a universal profile that only depends on the fractional diffusion. It's the fractional diffusivity. Okay, it's the way you react. Okay. So that's it. Thank you very much.
Okay. There are some other questions or remarks?
So what about the Mesa problem in the other problem you mentioned?
The other
Does it
problem.
make sense?
The Mesa problem in that in the other problem, we
Yeah.
didn't do anything, no, because we only in the paper, let's say the model number 1, I was doing only m equals 2, u gradient u. So I am not doing m's. If you put m's, these are very complicated, and you can do that. But the real problems in the model number 1 was now understanding the behavior of free boundaries. And they have this bad regularity that has to be understood. Maybe you can help in doing that. There are lots of literature that has been compiled, and I can give it to you references. Not on these things because they are open, but the rest of the things about theory of regularity, comparisons, whatever is more or less written. There are like this is 30, 40 pages of these papers on these things by different people.
Other questions?
Can you say anything about convergence to radially symmetric?
In the case of the model 2, if M is fixed, I can prove that any initial data converges to the Barenblatt profile. This can be done, which is the typical result. So the Barenblatt profile will be attractive. In the model 1, it is proved by entropy methods. In the model 2, it's proved by comparison. So the technique is different. And there are 2 papers on that are on my webpage. One of them, the convergence as t tends to infinity in model 1 is a paper with Caffarelli and Vasquez number 2. And convergence as t tends to infinity in model 2 is a paper that is in archive and will appear in Journal of the European Mathematical Society by myself. One of the models has comparison, another one doesn't have comparison, but it's a good flow in entropy methods. So you can use entropy.
So in model 1, you just deal with the case of the existence of the free boundaries for M equals 2 only.
That we have proved that if you put different M's, there are free boundaries in one case and not free boundaries in other cases. This is already more or less understood. But nothing is done about the regularity of the free boundaries. What we have understood recently with my students, 2 guys who were here, Del Peso and Diana Stan. We did a model 1 with M different than 2 to see if there is finite preparation or not. There is a preprint of the Newton Institute. I mean, the problem of regularity is maybe not very difficult, I don't know. I have a tendency not to do it. Because I cannot, let's face it. So, but maybe some of you guys say, listen, I can do that. I cannot invite you, if you solve it in 2 weeks, I should offer you a ticket for the final of the European Champions, but maybe it's too expensive. Even if Real Madrid plays, it's too expensive.
Maybe his stadium is not ready yet.
Okay.
Any other questions? Let's thank Juan Luis again.